This is the Sun, the brightest and closest star in our sky. Every second, it converts around 4 million tons of matter into pure energy, providing the main source of energy for life on Earth. But the Sun is just one star among many, as evidenced by thousands of flickering dots of light in the night sky. Stars like the Sun are also not the most common type of star in our galaxy. By some estimates, about 3/4 of all the stars are in fact red dwarf stars, also known as M-dwarfs. Importantly, planets are abundant around M-dwarfs, and the vast majority of Earth-sized exoplanets that have been discovered so far orbit M-dwarfs, as opposed to Sun-like stars. How does this affect our chances of finding another Earth? In this video, I will summarize the main differences between stars like the Sun and red dwarfs, as well as how these differences may affect the habitability of potential Earth-like exoplanets. Red dwarfs are the smallest and coolest stars on the main sequence. Their masses vary roughly between 8% and 60% of the mass of the Sun. They are, however, much less luminous compared to the Sun. The total energy output of any M-dwarf is at most 10% that of the Sun, while the smallest M-dwarfs can be over 1,000 times fainter than the Sun. As their name suggests, red dwarfs produce most of the radiation in the infrared part of the energy spectrum, and would appear red in hue to the naked eye. We shall now take a look at a real planetary system around a nearby M-dwarf. LHS 1140 is a typical low-mass red dwarf. It is in the constellation of Cetus, at a distance of 49 light-years from us. Its mass is less than 1/5 of the mass of the Sun, and it is over 200 times less luminous than the Sun. It is notable for hosting 2 terrestrial planets. Both of these planets are larger than any terrestrial planet found in the solar system, and are therefore classified as super-Earths. Similar super-Earth-sized planets have been found to be a common occurrence around M-dwarfs. The inner planet, over twice the size of the Earth by volume, circles the star on a close-in orbit, completing one full trip around the star in just over 90 hours. Its closeness to the star, however, likely renders the planet too hot to be habitable, with estimated day-side temperatures rising above the boiling point of water. The outer planet is the larger of the two. It is 7 times more massive than the Earth, and over 5 times larger by volume. Despite having an orbital period of only 24.7 days, the planet receives half the total amount of energy Earth receives from the Sun, due to the very low luminosity of the host star. Thus, it could feasibly sustain water in a liquid or frozen state on its surface. In general, habitable temperatures can arise on planets orbiting M-dwarfs at much shorter orbital periods compared to the 1-year orbit of the Earth, as these stars are much less luminous than the Sun. Shorter orbital periods, however, introduce another problem. When a planet orbits too close to the star, tidal forces tend to synchronize the planet's rotation around its own axis with the orbital period, leading to tidal locking. Just like the Moon always faces the Earth with the same side, tidally locked planets have one side of the surface permanently illuminated, while the opposite side is saddled with eternal darkness, leading to drastic temperature differences between the day side and the night side. Such planets would be prone to dry and bare day sides and frozen night sides, although atmospheric circulation could help redistribute heat between the two sides. Most planets that receive the right amount of energy from a red dwarf to be potentially habitable are also likely to be tidally locked. Another potential setback to planetary habitability arises from stellar variability. Young stars are known to exhibit strong magnetic activity, as well as high X-ray and ultraviolet emission. The lowest mass M dwarfs can remain in this magnetically active phase of their evolution for billions of years, much longer than Sun-like stars. Intense XUV radiation can erode planetary atmospheres, as well as cause water loss from the planetary surface. The long-lived violent nature of young M dwarfs is evident in TOI 540, a highly active low-mass star, 46 light-years from Earth. It hosts a Venus-sized planet on a 30-hour orbit around the star. While there is no data on whether this planet has an atmosphere, it is most likely a barren rock due to its small size and the intense radiation environment created by the star. By recent estimates, as much as 1/3 of the nearby lowest mass M dwarfs still exhibit high magnetic activity, despite likely being billions of years old. Despite these challenges, the presence of life cannot be ruled out on planets orbiting red dwarfs. Perhaps some of them have been able to retain atmospheres and magnetic fields that mitigate the effects of stellar radiation. Or perhaps life on these planets is more adapted to extreme environments. On the positive side, it is easier to detect and study planetary atmospheres around M dwarfs due to the planets being relatively larger in size compared to their stars. This is one of the main goals of the James Webb Space Telescope that entered service in July of 2022. Red dwarfs remain the most abundant type of star in the galaxy, and we expect to make substantial inroads into understanding the potential habitability of planets orbiting these stars in the near future.